Alright, so what we need to do now is worry about giving the statements of and of course the proofs of Montel's theorem and Marty's theorem in the case when the domain includes the point at infinity. Okay, so if you recall, see, all this time we have been worrying about domains in the complex plane, but since the last lecture we also wanted to include the infinity as a point in the domain. That means you are looking at a domain in the external complex plane. Alright, see, the problem with including infinity is that compact neighborhood of infinity makes sense only in the extended plane. Okay, and because it corresponds to a compact neighborhood of the north pole on the Riemann sphere, the extended plane being identified with the Riemann sphere. Okay, so but if you take a compact neighborhood of infinity and delete infinity, okay, then what you will get is you will get an unbounded domain in the usual complex plane. So basically it is an unbounded domain and along with of course the boundary. So on an unbounded domain we generally do not expect uniform convergence. Okay, we expect uniform convergence only on bounded domains, especially on compact subsets. Okay, and of course compact implies closed and bounded. So and since you are in Euclidean space, it is the same as closed and bounded. So you should not expect uniform convergence on an unbounded domain. Okay, that is the rule. You will get it only on compact subsets. So if you take a compact neighborhood of infinity, okay, then you will see that it is too much. In general, it is too much to expect uniform convergence because it's unbounded as far as if you look at it from the complex plane point of view, any compact neighborhood of infinity, for that matter any neighborhood of infinity will be an unbounded set in the usual complex plane. Okay, it will be bounded only with respect to the external complex plane. Okay, so that is the reason why we defined what is meant by normal convergence, what is meant by normal uniform convergence of a sequence or normal convergence of a sequence of functions defined on a domain which contains the point at infinity. Okay, so the way we did it was, if you remember, if D is a domain in the external complex plane, of course if the and of course if infinity is a point of the domain, then what you do is that you consider two things. You first of all remove infinity and you get D minus infinity, and that becomes a domain in the usual plane. And for such a domain, you know what uniform convergence on compact subsets, that is normal convergence, means. So you make that definition, and then to deal with the point at infinity, to deal with normal convergence at infinity, what you do is that you invert the variable. So what you do is you take a neighborhood of infinity, you take a neighborhood of z equal to infinity and treat it as a neighborhood of w equal to 0 by putting z equal to 1 by w. Okay, and then you say now this neighborhood of 0 is anyway it is anyway a neighborhood in the complex plane, so it makes sense to talk about normal convergence. Okay, so you define a sequence of functions to converge normally on a domain in the external complex plane containing the point at infinity if it individually individually it converges on D minus infinity, and the sequence with the variable changed from z to 1 by w converges normally in a neighborhood of w equal to 0, which corresponds to a neighborhood of z equal to infinity. Okay, and then with this modification we found that the limit function to which if the original functions are already continuous, for example, which is the case when you have analytic functions or meromorphic functions, then the limit function is also continuous, and the limit function is of course unique and continuous because it's a two-piece definition. There is a definition for the domain minus the point at infinity, and there is another definition for a neighborhood of infinity. Okay, so in principle you could have got two different functions, but because of continuity you will get a unique function, okay. And therefore what we did was we were able to extend these important results, namely that if you have a sequence of analytic functions on a domain in the external complex plane, if that sequence converges normally on the domain, then the limit function is either analytic or it is identically equal to infinity. And we also proved the same thing for meromorphic functions. If you have a sequence of meromorphic functions on a domain in the extended plane, and if that sequence converges normally, then the limit function is either meromorphic or it is identically equal to infinity. Now what we need to do is we need to worry about Montel's theorem and Marty's theorem, which is a meromorphic version of Montel's theorem, to in the case when the domain of definition of the functions or family of functions is a domain in the external complex plane, okay. So for that we will have to define what is meant by normally sequentially compact for a family of functions defined on a domain in the extended plane, and that involves a little bit of subtlety, but anyway as we will see, everything works out well. So let me write this down. So suppose D in the external complex plane is a domain, of course non-empty, it's an open connected set, and let's assume that infinity is a point of T, okay. So so this means that if you remove infinity from D, what you will get on the complex plane is an unbounded domain, okay. And what we want to do is suppose you have a family of functions defined on this domain, I would like to say what it means for the family to be normally sequentially compact, okay, because after all Montel's theorem, the usual Montel's theorem and Marty's theorem are just the correct generalizations of the Arzel-Ascoli theorem, okay, which say that so Montel's theorem says that for analytic functions normally sequentially compact, okay, that is sequential compactness with respect to normal convergence, that is the same as uniform boundedness on compact subsets, that is normal uniform boundedness for the family, okay. And Marty's theorem extends this from analytic functions to meromorphic functions, okay. So one can always be very naive and say that, well, my definition of a family F being sequentially compact with respect to normal convergence is just that it should be sequentially compact with respect to normal convergence when infinity is removed, okay. So on the domain punctured at infinity, and to deal with the point at infinity you say that the same family, you take the same family and change the variable to from z to 1 by w, and you say for this new family defined in a neighborhood of 0, again you should have sequentially compact with respect to normal convergence, and this is the definition that you will make in line with what we have been doing, and if you will see that it's the correct definition to make, okay. So let me write this down. We say that a family script f of functions on D with values in C union infinity, that is the external complex plane, is normally sequentially compact, i.e. sequentially compact with respect to normal convergence if number one, so F is normally sequentially compact on the domain D punctured at infinity, and now I will have to take care of the point at infinity, and for that what I will do is that f, let me put this as f sub 1 by w, this is the set of all f of 1 by w where f belongs to script f. So I put the subscript 1 by w to tell you that I have changed I have inverted the argument, the independent variable in the function, okay, is normally sequentially compact on a neighborhood of w equal to 0, because you know a neighborhood of w equal to 0 will correspond to a neighborhood of z equal to infinity, because w is 1 by z, alright. So this is the so I should put this heading as normal sequential compactness for a domain in the extended complex plane. So that is the heading, right. So well, this seems to be the right definition to make. Whenever you want to deal with a domain which contains a point at infinity, you deal with it in two pieces. One is you throw the point at infinity, okay, you throw it away, namely you puncture the domain at infinity, so you get a deleted neighborhood of infinity, and you give a definition for that, and that is easy to give because a deleted neighborhood of infinity is also a domain in the usual plane, okay. And the other thing that you do is that to consider a neighborhood of infinity, you consider a neighborhood of 0 by inverting the variable, okay. So well, now, so there are a couple of things that I want to tell you with respect to the notation, terminology and literature, and also there's another subtlety that I want to point to you about. So the first thing is that, you know, in the literature this normal sequential compactness is actually abbreviated to normal, okay. So this is a very important thing. See, people just use the word normal. This is in fact Montel's terminology, that instead of every time saying normally sequentially compact, you use the word normal, and this is considered as this is being thought of as a property of the family. So when you say a family is normal, it means it's not normally sequentially compact, okay. So so wherever normally sequentially compact comes, you know, then you can just replace it with the word normal, okay. And the whole point is that a family being normal is the correct notion of compactness of a family, okay, that is the whole point, okay. So you know, if you are working with general topology, and if you are working with continuous functions, say real valued or complex valued functions, and you are working on a you know, compact metric space, or for that matter you are even working with continuous functions with taking values in from one compact, I mean it takes values in another compact metric space, okay, then usually compactness, because you are in the context of metric spaces, compactness is the same as sequential compactness, okay. So and there what happens is that when you say sequential compactness, the idea is that you are able to say that every sequence admits a convergent subsequence, okay, and this convergence is with respect to what it's with respect to for example if you are working with real or complex valued functions, it's with respect to the supremum norm, okay. So there is a supremum norm which induces a metric and its convergence with respect to that metric, okay. But of course when we are considering the extended complex plane, we are using the spherical metric, that is one thing that you must always remember, okay. The extended complex plane is a compact metric space, and the metric you are using on that is a spherical metric, okay, which is actually a spherical metric on the Riemann sphere transported to the extended complex plane, okay, by the identification of the Riemann sphere with the extended complex plane using the stereographic projection, okay. Now the point is that this is what you will get if you are looking at continuous functions. But if you are looking at analytic functions, the rule is that you cannot expect uniform convergence on unbounded sets. You can expect uniform convergence only on compact subsets, and this is called normal convergence. Okay, so when you are in the context of analytic functions or in the context of meromorphic functions, okay, then you have to worry only about uniform convergence on compact subsets, and that's called normal convergence. Okay, and you have to do everything normally. Okay, and the point is, therefore, in the context of analytic functions or meromorphic functions, the correct notion of compactness is not sequential compactness, but it is sequential compactness restricted to compact subsets, and that's called normal sequential compactness. And Montel's terminology is that you don't say normally sequentially compact, you simply say normal. Okay, so so this is one this is something about terminology that you must know. Then the other thing is of course about the subtlety in talking about normal sequential compactness. The subtlety is, you see, when you say normally sequentially compact, it means that it is sequentially compact when restricted to compact subsets. And what does sequentially compact, I mean, if you blindly read for any property P, normal P means the property P is supposed to hold when restricted to compact subsets. So if you go by that, normally sequentially compact will mean that it will mean that it is sequentially compact when restricted to compact subsets. So what does that mean? It means that you give me a sequence, okay, then if you restrict it to a compact subset, I will get a convergent subsequence. Okay, but if I restrict to different compacts, if I start with a given sequence, okay, of functions, and if I restrict to different compact subsets, I may get different convergent subsequences. Okay, but the fact is there is it's more than that. You can get uniformly a subsequence which will converge on every compact subset, and this is actually another diagonalization argument that we used. If you check, so actually this normally sequentially compact is as strong as sequentially compact with respect to normal convergence. Okay, sequentially, when you say sequentially compact with respect to normal convergence, what you mean is that given a sequence I can find a subsequence whose convergence is normally convergent subsequence, which means that same subsequence will converge on when you restrict to any compact subset. But when you say normally sequentially compact, you might interpret it as give me a sequence for every compact subset, I will get a convergent subsequence. But it looks as if you change the compact subset, the convergent subsequence could change. But the truth is that there is not much difference, because you can use always a diagonalization argument. Okay, and you can use a sequence of compact subsets that fill out an increasing sequence of compact subsets that fill out your domain. Okay, that's the argument that we used. So there is really no confusion in saying normally sequentially compact and sequentially compact with respect to normal convergence. There is really no difference. Okay, that's because of this diagonalization argument that you can apply on a sequence of increasing sequence of compact subsets that can cover your domain. Okay, so that's one subtlety. Then here comes the other technical issue. The technical issue is that again because you are dealing with the point at infinity, we have defined normality in two pieces. We have defined normality outside infinity, that is the first requirement, and the second requirement is normality at infinity. Okay, now think of it for a moment. What does it mean? It means, suppose I start with a sequence in my family, the normality outside infinity will give me a subsequence which will converge on compact subsets outside infinity. Okay, and what will happen is, separately for the same sequence of functions, I will get another subsequence which will converge normally at infinity. Okay, now I seem to be getting two different subsequences. Okay, and I don't seem to be getting a single subsequence which will converge both outside normally outside infinity and also at infinity. I don't seem to be getting that, and the fact is that you can do this. Okay, it's not much of a discrepancy, because you see, suppose you have a family script f which is normal in this sense. Okay, what you do is start with a sequence in the family. Okay, first go to a neighborhood of infinity. Okay, go to the second condition, namely you go to a neighborhood of infinity which is thought of as a neighborhood of 0 with the variable inverted, there you first pick a subsequence which is which converges normally at infinity, okay. Then what you do, this subsequence is also anyway a subsequence of the original family which is normal outside infinity, okay. So take the same subsequence and now apply it to the domain outside infinity, and you get a further subsequence which will converge normally outside infinity. So that's this new subsequence that you picked up, that will be one which will converge both outside infinity and at infinity, okay. So even though you are doing it piecewise, everything works out fine, okay. So you do get a global give me a sequence, you do get a global subsequence, okay, which will converge normally both outside infinity and at infinity, okay. There's no confusion, alright. Only thing is you have to do this twice, alright. So let me write that down. There is no ambiguity in the conclusion of normality for f for if f1, f2 and so on is a sequence in f which is assumed normal on D, then we first pick a subsequence fn1, fn2 and so on that converges normally in a neighborhood of infinity, which means that fn1 of 1 by w, fn2 of 1 by w and so on converges normally in a neighborhood of w equal to 0. This is what it means, okay. And then we pick a further subsequence of this subsequence so fn I1, fn I2 and so on, which also converges normally on D minus infinity. Then then this subsequence fn I1, fn I2 so let me use is a subsequence that converges normally on D, okay. So there is no problem, alright. You are able to get one subsequence that will work both outside infinity and at infinity, okay. So this is a little fact that you need to know. So we see this is just part of the usual philosophy in mathematics. So there are two things I want to say. Usually what happens is good properties of functions hold on open sets. The other thing is to verify that a good property is true, you verify it only locally. That means you can verify it at each point in a neighborhood of each point or on an open cover, okay. For example, this is the case with continuity, okay, or analyticity and so on, okay. Good properties, if you want to check a function is analytic, you check at each point or in a neighborhood of each point. If you want to check a function is continuous, it's enough you check at each point, okay. So in the same way, you see this normal the idea of a normal family is also local, okay. If you say that a family is normal in pieces, okay, that is it's normal on an open cover, alright, then it continues to be normal. So for example, what we are saying is that if a family is normal outside infinity and if a family is normal in neighborhood of infinity, okay, this outside infinity and neighborhood of infinity together constitute a cover, okay, and for the whole domain. And when you say the function is normal outside infinity and at infinity, okay, then you are getting it is normal on the whole domain, okay. So you see, normality is a local property, that's what is happening, alright, and it's a good property, and all good properties are usually local properties. You can verify them locally and they are valid on open sets, okay. So this is something that you should remember as a philosophy. Now so this should have been normally, alright. Okay, so now what I am going to do is now let's go on with now with this background, it's very easy to write out the analog of Montel's theorem and Marty's theorem for domains in the extended complex plane, okay. So here is Montel's theorem. So here is Montel's theorem. So let me put it as for domains in the extended complex plane. What is the theorem? The theorem is let script f be a family of holomorphic or analytic functions on a domain D in the extended complex plane, then script f is normal if and only if script f is normally uniformly bounded. Okay, so this is Montel's theorem, okay, where you say that normality of the family is the same as normal uniform boundedness of the functions in the family, alright, and mind you, normality in the family means that it's normally sequentially compact, that is, it's sequentially compact with respect to normal convergence, alright. Every sequence admits a subsequence which converges normally, that is, a subsequence which converges uniformly on compact subsets, right, and normally uniformly bounded is uniformly bounded on compact subsets, alright, and this normally uniformly bounded on a domain in the extended plane, again how do you define that? You define it piecewise. So what you say is that if you want to say a family of functions is normally uniformly bounded on a domain in the extended plane, what you do is that you first say that it is normally uniformly bounded when you throw out infinity, so it should be normally uniformly bounded on D minus infinity, and then you say that the corresponding family with the variables inverted, okay, is normally uniformly bounded in a neighborhood of 0 for the inverted variable, which corresponds to the neighborhood of infinity for the original variable, okay. So this normally uniformly bounded also needs to be defined when you consider the point domain which contains the point at infinity, but again you define it in two pieces. You make one definition outside infinity, and then at infinity the definition you make is by inverting the variable and so that you change z equal to infinity, a neighborhood of z equal to infinity, which is a neighborhood of infinity, you change that to a neighborhood of w equal to 0 where w equal to 1 by z or z equal to 1 by w, okay. So this is Montel's theorem, and you can see that the proof of this theorem just comes from the usual Montel theorem, because finally what you have done is you have to deal with the point at infinity, you are actually going back to 0 by inverting the variable, alright. So the moral of the story is that by this device you are able to deal with the point at infinity. So the proof of this Montel theorem will follow from the usual Montel theorem, okay, and of course you have to worry about one thing, namely that when you come from normal uniform boundedness to normality, okay, what you will get is that you will get separately normality outside infinity and you will get separately normality at infinity, but we just now discussed that normality is a local property, so you will get normality on the whole domain, okay. So so everything works out fine, alright. The only thing that I want you to remember is that at the back of all this, how does this differ from the usual Arcelor-Ascoli theorem? The usual Arcelor-Ascoli theorem says that, you know, if you want compactness, then it's the same as sequential compactness, and that is equivalent to, you know, uniform boundedness and equicontinuity, okay. So you need equicontinuity, alright, and of course the usual Arcelor-Ascoli theorem is for functions defined on compact metric space, but then here you are working with functions on a domain, it's certainly not a closed set, okay, it's an open connected set, and therefore what you will have to do is that you will have to go from usual convergence, you have to go to normal convergence. So you have to, you must instead of expecting uniform convergence on the whole domain, you should expect only uniform convergence on compact subsets of the domain. And then the big deal is, as usual, you know, you don't have to worry about equicontinuity, because equicontinuity is automatic. In the case of analytic functions, you know, if the functions are original functions are bounded, then the derivatives also become bounded, and that is because of the Cauchy integral formula and the Cauchy estimates for the first derivative, which can be expressed as an integral of the original function, okay. Therefore if you have normal uniform boundedness of the functions, then you have normal uniform boundedness of the derivatives, and normal uniform boundedness of the derivatives always implies equicontinuity, okay. So you get equicontinuity for free, okay, and therefore the only important condition is the uniform boundedness, normal uniform boundedness of the family, okay, and that is the whole point about Montel's theorem. And then the extension of this theorem to meromorphic functions is of course Marty's theorem, so that also works, okay. But the point is that, you know, when you go to Marty's theorem, you will have to worry about not using the usual derivatives, because at what you are working with are meromorphic functions, and at a pole they are not differentiable, okay. And then, you know, the trick is to not use the usual derivatives but use the spherical derivatives, okay, and then you get the analog of Montel's theorem for meromorphic functions, okay, and that is Marty's theorem. So let me write this down. So here let me just mention that the proof follows from the usual Montel theorem. For domains in the complex plane, and our remarks above, okay, and then now let me go on to Marty's theorem. In Montel's theorem, you know, you can allow the functions to take only complex values because they are analytic functions, okay. There is no question about taking the value infinity, alright. So whereas if you go to Marty's theorem, you are considering meromorphic functions, and to make such a function continuous at a pole, you define its value at the pole to be infinity. So you will have to necessarily look at functions with you know values in the extended complex plane, okay. So so here is a statement similar to the statement of Montel's theorem. So in Montel's theorem we said f is a family of holomorphic functions on a domain D in the extended complex plane. Now you will say f is a family of meromorphic functions on a domain D in the extended complex plane, okay, but taking values in the extended complex plane. You will have to say that, okay. And then you also say that then of course the statement is that the family is normal if and only if the family of spherical derivatives is normally uniformly bounded, that is the theorem. Okay. So, let me write that out. Let script f be a family of meromorphic functions on a domain D in the extended complex plane, taking values in the extended complex plane then this family is normal if and only if the corresponding family of spherical derivatives, namely you take the spherical derivatives of the functions in the original family, is normally uniformly bounded. Okay. So, this is Marty's theorem. So, again let me pinpoint a couple of things. The first thing is that the reason why I am repeating this several times is I want you to note that there is a I want you to note these important differences. See, when you are looking at meromorphic functions, necessarily you will have to use values in the extended plane for two reasons. The first reason is that you want the meromorphic function to be continuous at a pole. So, you define the value at the pole to be infinity, okay. That is one thing. The second thing is that in the target space you want to have a metric, okay. So, you know, I want to a function, if you are looking at a meromorphic function at a pole, it can take the value infinity, okay. So, I will have to compare infinity, the value infinity, with finite values, with finite complex values, and the only way I can do that is by using the spherical metric which is available on the extended plane. So, it is very important that you have to take values in the extended plane and you have to use a spherical metric, okay. This has to be done if you are working with meromorphic functions, okay. And then the other important thing is that you need to worry about not the usual derivatives but the spherical derivatives. Usual derivatives of course will not work because usual derivatives will not, they will not even be defined at a pole, okay. So, you will have to work with the spherical derivative which is defined even at a pole, and I told you there is no problem with the spherical derivative, it is always continuous, and even at a pole it is defined by continuity. The pole is a simple pole, then the spherical derivative is 2 divided by the modulus of the residue at that simple pole for that function, and if the pole is a pole of higher order than the spherical derivative is 0 at that pole. So, and this is done in a very continuous fashion, alright. So, the point is the spherical derivative is a continuous function, continuous non-negative real valued function, and these are the functions that we have to ensure the uniform boundedness of these spherical derivatives, okay, when restricted to compact subsets, okay. Now, that is normal uniform boundedness of spherical derivatives is what we want, and that is the equivalent condition to the original family being normal, namely that the original family you know, is normally sequentially compact, okay. So, this is Marty's theorem, right. Now, so you know, this brings us to a very important point, namely at this point you are able to get all the theorems that you want, okay, by including functions which can take the value infinity, okay, namely meromorphic functions, and you can also have functions defined at infinity, okay. So, what you must understand is that all these lectures, all the tools that we built were to tackle two things. First of all, you wanted to tackle the function in a neighborhood of infinity, okay. That means you wanted to study function in the neighborhood of the point which is infinity. For example, that is why we initially were worried about trying to define when infinity is an isolated singularity, and if it is an isolated singularity, is it what kind of singularity it is, okay. And the trick in all these cases was to replace a neighborhood of z equal to infinity by a neighborhood of w equal to 0 where w equal to 1 by z, okay. And you must understand that this z going to w, that is kind of it's a homeomorphism, okay, of the Riemann sphere onto itself. If you want, it's a self homeomorphism of the extended plane onto itself, which you can think of it also as a isomorphism of self homeomorphism of the Riemann sphere onto itself. And what happens is that the infinity is is identified with the north pole, origin 0 is identified with the south pole, okay, and it's just this the inversion is just switching the north and south poles of the Riemann sphere, okay, and this inversion is a very nice thing. It doesn't change the spherical distance, because essentially inversion corresponds to a rotation of the Riemann sphere by 180 degrees with respect to the real axis, the x-axis, okay. So the point is that you can deal with the point at infinity, okay, that is one aspect. Then the other aspect is you can deal with these functions which have poles, namely meromorphic functions, by allowing the value infinity, okay. So on the whole we have built up all these tools to deal with meromorphic functions. Even so, you can look at a family of meromorphic functions even defined in a neighborhood of infinity and work with it, okay. That is the generality to which we have defined things, and now we will use all this in the next few lectures to prove the Picard theorems, okay. So I will stop here.